Now in these lessons, I'm going to walk you through examples that will help you be able to apply Gauss' law in calculating the electric fields of symmetric objects. In this example, we have been asked to calculate the electric field of this spherically charged object. Now remember that this object is solid, so we want to calculate the electric field everywhere. How do we use Gauss' law in calculating the electric field of this charged object? It is important for you to understand that when applying Gauss' law, there are some simple steps that you have to take in order to apply the law correctly. If you follow these simple steps, I can certainly guarantee you that you will get the problem right. Now, the very first step that you need to take is to draw your Gaussian surface in the appropriate region. So, let's start first by looking at case 1. Let's look at the region where r is less than the radius of the sphere. So if we pick a Gaussian surface r, this is our Gaussian surface. Now, what you need to understand is that the Gaussian surface is inside the sphere. Now, Gauss' law tells us that the flux E, phi E, which is given by the surface integral of E dot dA, is equal to the charge enclosed by that surface divided by epsilon naught, where epsilon naught is the permittivity of free space. So let's start first by determining the flux. In this case, phi sub E is equal to the closed integral of E dA, which is the same as E, the integral of A. Remember that this is constant. This is the same as E bracket by r squared. So we know that E 4 pi r squared is equal to Q enclosed divided by epsilon naught. This would mean that E is equal to Q enclosed divided by 4 pi epsilon naught r squared. But the question is, what is Q enclosed? To calculate the enclosed charge by this Gaussian surface, we need to make the fundamental assumption that the charge distribution over the sphere is uniform. If we make that assumption, then we know that the rho, which is the charge density, is defined as Q over V, where V is the volume. Because the distribution of charge over this sphere is uniform, we are free to say that this is equal to Q enclosed divided by V enclosed. This means that Q over 4 over 3 pi r cubed is equal to Q enclosed divided by 4 over 3 pi small r cubed. this takes care of this, and we end up with Q enclosed equal to the total charge on the sphere multiplied by R cubed, all divided by capital R cubed. This is the total charge enclosed. So what do we do next? What happens next is we will take this and substitute here. That means that E of R becomes equal to 1 over 4 pi epsilon naught squared R squared Q R cubed divided by capital R cubed. You realize that this takes care of one of that, and the E of R, which is less than big R, becomes 1 over 4 pi epsilon naught multiplied by Q R divided by R cubed. So this gives us the electric field inside the charged sphere. Remember, the very first step you need to do is draw your Gaussian surface. Then the next step is for you to calculate the flux defined by that Gaussian surface. When you calculate the flux defined by that Gaussian surface, then you have to look at and answer this question: what is the enclosed charge by that surface? When you calculate the enclosed charge by that surface, then all you have to do is substitute that into the equation of the flux, and there you will get your electric field. The next scenario is for us to look at case 2, at which point R will be greater than big R. So if we pick a Gaussian surface way out here, of radius R, we know that from Gauss' law, the flux is equal to the closed integral, which is a surface integral, of E dot dA. This will be equal to, the E is constant, so we could take it out. So this is just E, the integral of dA, which is just going to be E bracket 4 pi R squared. That means that 4 pi R squared multiplied by E is equal to the charge enclosed divided by epsilon naught. The charge enclosed is just Q. So this is Q divided by epsilon naught. Hence, E, which is greater than R, will be equal to Q divided by 4 pi epsilon naught R squared. So this right here is the electric field within the sphere, and this right here is the electric field outside the sphere. One of the things you need to take note is the electric field within the sphere, E, is proportional to R, but the electric field outside the sphere, E, is inversely proportional to R squared. So if we draw the electric field, how it varies, this is the radius R. It will begin from 0 at the origin, increase linearly to maximum on the surface, and then decrease inversely. So E is proportional to R there. E is inversely proportional to R squared out here. This is the electric field measured in coulombs, newtons per coulombs, and this is the distance R measured in meters. Thank you, and see you next time.